as far as computer graphics is concerned, I don't care about most of the fancy math properties that homogeneous coordinates have. I care about the fact they let us play a math trick to make our math convenient. So the idea is I'm going to add a coordinate. So we want to do 2D points. We're going to use 3 values. So we're adding a dimension just because. So if I have an xy point, I'm going to write xy1. I'm just going to add this extra dimension. And this means I'm going to need 3 by 3 matrices to work on these now 3 vectors instead of the 2 by 2 matrices we had before. And at the end, I have to do something to get back to my real x and y. So I'm going to get, we call this last homogeneous coordinate a w. So we're going to end up with xyw. We're going to multiply our point times some 3 by 3 matrix. We're going to get this. And then we're going to do what's called a perspective divide. We're not up to perspective yet. So far, our w is just going to be 1. But you should know to get to the real x and y, that's going to be the position on the screen, we have to divide by this w. So it seems like we've just made things harder by adding this divide, but you're going to see that it's going to allow us to stack up our matrices. So this is the trick. We add a coordinate. So here's our matrices that we had before. And here's an example. So we had scale, was just this top left corner previously. So we've made it up to a 3 by 3 matrix, and we've just filled in 0s and 1s. Same thing for rotation, filled in 0s and 1s. So if we take a point, our xy point with a 1 added, so this is a homogeneous 2D point now, multiply times our scale matrix, we're going to end with the scaling factor for x, the scaling factor for y, and 1. Or we're going to divide by this 1, and we're just going to get back what we wanted. So nothing too exciting has happened so far. We've just added a dimension. It's just a pass-through. It just disappears. When we eventually talk about perspective, it's going to be more exciting on this W, but that's going to be, I don't know, 4 or 5 lectures from now, so we won't get to that today. But what we are going to get today is translation. So here's a translation matrix. So now we're using this 3rd column that we've added into this matrix. So we have essentially an identity matrix with these added in. But what do we get when we multiply? So the identity matrix carries through our x's and y's, but this 1 in this last component adds in whatever these delta values were, right? Because remember when we multiply, this is xx times 1 plus xy times 0 plus 1 times bx. So we end up with this vector, xx plus bx. I realize the notation's switching around, right? So this is the original x, or this is the output x, right? This is the original x, this is our output vector. It used to be called prime in a different slide. So homogeneous coordinates have made it so that we can write it in this multiplicative form. So now we're back to being linear, but in 1 dimension up. Wanted to do 2D, and we couldn't get it. So, but now we've got this nice matrix operation happening in 3D. Okay, so here's the same matrices we saw previously, but now written in this homogeneous coordinates form. So our vectors always have this extra 1 hanging out at the end. We can write down this 3 by 3 matrix, and we'll get outputs, which are the outputs we wanted to get for our rotation and scaling and translation. They're not too much harder to remember because you can think about your rotation and scaling is just this upper 2 by 2, right? It's the only thing that's going on, and the rest is just filled in. And translation is these coordinates over here. Now, do you have to know what's in all of these matrices? Normally in this class, I make people memorize these matrices in order to take quizzes and do other things. But in this class, because everything is open book, you're obviously not going to have to memorize. What's important, though, is that you know how to take a point and you can understand why that point is ending up in a new location. So when you write your code, of course, this is hidden from you, what's in this matrix. But I think that if you don't understand what's in this matrix, it's going to make it hard to make your code do the right thing and thinking about how these things are composed. So even if you don't fully get it now, I encourage you when you go to do the homework later to actually think about what's in these matrices and why is it that way. So let's just look at some examples. So here, instead of drawing a square, I've drawn some other shape. But remember, this shape is made out of triangles, and there's vertices on these triangles. So this is all linear transformations. So we've got, and this is why we can still remain in 2 by 2. So we have scaling, non-uniform scaling. Here's a rotation, right? And remember that these numbers, these cosine theta, sine thetas turn into numbers, right? According to what the theta is. A negative scale turns out to be a reflection. If we go up a dimension, Now we can get translation. So now we're on 3 by 3 matrices. So now I can move my objects with a translation matrix, but I can still write my scales and my rotates in this 3 by 3 form.